Good day, everyone. This report discusses the fire and explosion risk associated with fine powders and their significance in engineering operations. Let's start off with the table of contents. First, introduction. Second, the combustion of fundamentals. Third is the combustion in dust clouds. And lastly is the control of the hazard. Fine powders, also known as combustible dusts, can ignite or even explode when dispersed in air under the right conditions. These risks arise because fine particles have a large surface area relative to their volume, allowing them to react rapidly with oxygen. Dust explosions have caused serious property damage and loss of life across various industries such as food processing, metal fabrication, and chemical manufacturing. Understanding these risks is essential for engineers to ensure safe plant design, hazard prevention, and worker protection. The hazards presented by fine powders can be classified into two main risks. Fire, when fine powders can easily ignite because of their large surface area, which allows rapid oxidation when exposed to air. Even a small spark, hot surface, or static discharge can start a fire once the dust is heated above its ignition temperature. Explosion, when combustible dust becomes suspended in air at the right concentration. It can form a flammable cloud. If ignited, the burning particles release heat and pressure rapidly, leading to a dust explosion that can cause severe damage and secondary blasts. Fine powders are commonly handled in many industrial sectors, including food processing such as flour, sugar, and grain handling, metal processing involving aluminum or magnesium powders, plastics and pharmaceutical industries, and energy and chemical plants handling coal or biomass. These processes often involve grinding, drying, conveying, and packaging, which can generate dust clouds and increase explosion potential. Common ignition sources and equipment include storage silos, dryers, and dust collection systems, conveyor belts, bucket elevators, and mills, and hot surfaces, friction, or electrostatic discharges from machinery. If not properly controlled, these systems can easily create conditions that can lead to ignition and combustion. A well-documented example is the Imperial Sugar Company explosion in Port Wentworth, Georgia, USA in 2008. In this incident, fine sugar dust accumulated on floors, equipment, and overhead surfaces. When the dust inside an enclosed conveyor came into contact with an overheated bearing, it ignited and caused a primary explosion. This initial blast disturbed more settled dust throughout the facility, leading to massive secondary explosions that destroyed much of the plant. The disaster resulted in 14 deaths and 38 injuries. Investigations revealed several key issues: poor housekeeping that allowed dust buildup, inadequate ventilation and dust collection systems, poor maintenance of machinery, and lack of worker training and hazard awareness. This tragedy highlighted how small ignition events can rapidly escalate when fine powders accumulate and engineering controls fail. From an engineering perspective, understanding and managing dust explosion hazards is critical for process safety. Engineers must design safe systems, including proper dust collection, ventilation, and explosion venting. Implement preventive maintenance, ensuring equipment remains clean, grounded, and free from ignition sources. And provide training so that all personnel understand proper handling, cleaning, and emergency procedures. Following safety standards, such as those from the Philippine Integrated Fire Protection Organization, helps ensure facilities remain compliant and secure. By combining good design, maintenance, and safety culture, engineers can effectively prevent dust-related fires and explosions, protecting both people and industrial operations.
Good day. Now that we have learned the dangers of dust explosions, we need to understand the science behind them. We will start with the fundamentals of combustion. We begin with the foundational model called the fire triangle. This heuristic establishes the three stoichiometric and energetic prerequisites for typical combustion: the fuel, the oxidizer, which is usually atmospheric oxygen, and the ignition source to supply the activation energy. For sustained combustion, however, we must use the fire tetrahedron. The fourth component added here is the uninhibited chemical chain reaction. This element represents the continuous production of highly reactive intermediates, specifically free radicals, which sustain the self-propagating exothermic nature of fire. Effective suppression, therefore, can target any of these four components. When dealing with dust hazards, a new model is required: the dust explosion pentagon. This model integrates the fire triangle with two critical physical parameters that differentiate a rapid combustion event from an explosion. The first is dispersion, which says that solid fuel must be suspended in the oxidant, which is air, at a specific concentration to form a uniform flammable cloud. This dramatically increases the reactive surface area. Second is confinement, which says that the reaction must be constrained within an enclosure. This confinement is what allows the rapid thermal expansion to translate into a dangerous, destructive pressure wave. Chemically, combustion is defined as an exothermic oxidation process. The general equation for an organic fuel is presented here. The key output is heat, which regenerates the ignition source and sustains the chain reaction. It is important to recognize that this is the equation for complete combustion only. In environments with insufficient oxygen, which is a common scenario in large vessels or dusty systems, incomplete combustion will occur. This results in the formation of hazardous byproducts like carbon monoxide, increasing fire risks and personal safety risk. The reaction of combustion is bounded by concentration limits. For dusts, we characterize this range using the minimum explosible concentration, or the MEC. The MEC represents the lowest concentration of airborne dust capable of propagating a flame front. If the concentration is well below the MEC, the mixture is too lean to support combustion, while an upper explosible limit, or UEL, exists for gases. A similar definitive limit is rarely observed for dusts. Instead, a highly concentrated dust cloud simply becomes too rich, where excess dust acts as a thermal sink, absorbing heat and inhibiting the necessary temperature rise. The regulatory goal is to ensure continuous operation at a concentration well below the established MEC for the material being handled. Finally, we need to understand the four main types of ignition sources, which provide the initial heat to start the reaction. Thermal ignition sources involve any hot surface, with the relevant parameter being the minimum ignition temperature. The surface temperature of any equipment must be maintained below the MIT to prevent ignition through direct contact or convection. Thermal sources include hot surfaces, which can arise from equipment malfunction, sparks, and open flames. Electrical ignition sources can come from short circuits, faulty wiring, or arcing in electrical contacts. Another major concern is the electrostatic sources. When fine dust moves through machinery, it builds up static electricity. This energy is measured by the minimum ignition energy, or MIE. Many industrial dusts can be set off by MIEs as low as 15 millijoules, which is less than the static shock you feel when walking across carpet. This makes grounding and bonding equipment absolutely essential to avoid explosions. Lastly, the primary source of chemical ignition is spontaneous combustion, occurring when certain dusts slowly react with oxygen at low temperatures, causing the material to heat itself up until it ignites. That will be the end for fundamentals of combustion.
Hello everyone, in this part of our presentation, we will explore the combustion in dust clouds, a phenomenon that's critical in understanding dust explosion hazards in industrial processes. Our discussion here will cover the mechanisms of deflagration and detonation, the characteristics of dust explosions, and the apparatus used to determine these parameters. Let's start first with the fundamentals of a dust cloud explosion. In general, finer combustible particles are more prone to explosion because they more readily form a dispersion with air, have a larger specific surface area, offer a greater surface area for reaction, generate more heat per unit mass, and have a greater heat-up rate. This concept is backed up by principles of chemical kinetics. As particle size decreases, the rate of heat generation increases, as shown in the equation for heat generation below, where the variable 6/x denotes that the heat generation is inversely proportional to the dust particle size. Or in other words, the smaller the particle, the more intense the combustion. This means that fine powders such as flour, coal dust, or metal dust can heat up and ignite much faster than coarser materials. To assess how severe a dust explosion can be, several key characteristics are determined experimentally. First, the minimum dust concentration for explosion. This is the minimum explosible concentration or the lower explosion limit. This is the lowest dust concentration that is suspended in air that can allow combustion. This is around 20 to 60 grams per cubic meter for common particulates in the industry. Second is the minimum energy for ignition, which is the lowest spark energy required to start off the explosive reaction. Particulate characteristics set the lower limit of this energy requirement. Third, the minimum ignition temperature, also called as the auto-ignition temperature, is the lowest temperature for spontaneous ignition without any external spark or any external flame. Fourth is the maximum explosion pressure, which is the peak overpressure generated during the explosive reaction. This is a crucial parameter, as we will see later in designing equipment handling dusts. Fifth is the maximum rate of pressure rise during an explosion, which indicates the robustness of an explosion. This is, again, we will see it later, used in designing relief systems or suppressive systems. Last but not the least is the minimum oxygen for combustion, as mentioned earlier, is the stoichiometric oxygen requirement to the lower flammability limit. This dictates the composition of air that may cause explosion. Together, these parameters describe how reactive and hazardous a dust material can be. Now we look at how combustion progresses once ignitions occur through the mechanisms of dust explosion. In deflagration, it is the rapid subsonic combustion of dust particulates below 344 meters per second, which is the speed of sound at ambient conditions. This type of reaction is driven by heat and mass transfer. The reaction front moves as particles ignite and release heat to their neighboring region. Easier ignition occurs when the minimum ignition energy and auto-ignition temperature are low. A higher maximum pressure and a faster rate of pressure buildup make the deflagration stronger and more destructive. On the other hand, detonation occurs when the combustion front moves at a supersonic speed, or greater than 344 meters per second. A shock wave compresses the unburned mixture, creating intense pressure and temperature spikes. Detonation happens only under special conditions, i.e., a dense and confined dust cloud near its optimum concentration. When the deflagration accelerates it to detonation, we call this a deflagration to detonation transition, or DDT, which occurs at low auto-ignition temperature and high max rate of pressure rise. To obtain the characteristics for dust explosions, laboratory scale test equipments are used. The simplest device is the vertical tube apparatus as shown in this slide. It consists of a vertical glass or metal tube with a dispersion cup at the bottom that holds the sample dust. Air is blown through the solenoid valve to disperse the dust into the tube, forming a dust cloud. Ignition can then be provided by either an electrical spark between electrodes or by a heated wire core. Here shown is the ignition electrode. This apparatus is mainly used for classification tests and for determining the minimum dust concentration for explosion, the minimum energy for ignition, and in a modified setup, maybe the minimum oxygen concentration for combustion. And although the setup is simple, the setup is fundamental for identifying whether a dust is explosible at all. For a more precise and safer explosion experiment, the 20-liter sphere apparatus is used, as shown here. This device is a spherical pressure vessel equipped with a pressure transducer. The test dust is stored in a small reservoir and is dispersed into the sphere by compressed air through the dispersion ring surrounding that vessel. The sphere is first evacuated to about 0.4 bar so that when the dust is injected, the pressure rises back to atmospheric pressure. Ignition is achieved using a pyrotechnic igniter, typically rated at 10 kilojoules, placed at the center. Delay between dust dispersion and ignition, which is about 60 milliseconds, ensures consistent turbulence level, which significantly affects the rate of combustion and the measured pressure rise. From these tests, we determine the maximum explosion pressure and the maximum rate of pressure rise, both of which are critical for designing an explosion protection system. Larger versions, such as the 1 cubic meter sphere, are used for scaling and validating these results. Finally, let's discuss how these measured characteristics are applied in the industries. First, the minimum dust concentration indicates the quantity of air to be used in the processing system for combustible dust. It helps engineers design ventilation and air handling systems that keep dust levels below explosive limits. Second, the minimum energy for ignition determines whether dust can be ignited by an electrostatic spark to as low as 15 millijoules. Third, the minimum ignition temperature dictates the maximum temperature for equipment and services in contact with the dust. Fourth, the maximum explosion pressure, which ranges from 8 to 13 bar, is used to determine the design pressure in vessels and pipes in explosion containment control. Fifth, the maximum rate of pressure rise during explosion is used in the design of explosion relief. This is related to the volume of the vessel by the equation shown below. Lastly, the minimum oxygen for combustion provides the maximum permissible amount of oxygen concentration when inerting, ensuring the oxygen levels remain too low for combustion to occur. Together, these parameters provide the quantitative foundation for explosion risk assessment and prevention.
Alright everyone, now let's talk about how we actually control hazards from fine powders. Because knowing explosions are dangerous in one thing, but preventing them, that's where engineering comes in. Our goal here is either to remove the conditions that allow a fire or explosion, or at least minimize their effect if they do occur. We'll look at two main approaches: engineering control, the physical stuff, and the administrative controls, the human and procedural side. First up, inerting. This one's simple but effective. We replace oxygen with an inert gas, like nitrogen or carbon dioxide. Since oxygen feeds combustion, removing it is like taking away the match from the fire triangle. It's commonly used in a closed system like silos or dryers. Next, ventilation. We can't always make everything airtight, so we use airflow to dilute dust concentration below explosive limits. Think of it like giving the dust particles too much personal space to cause trouble. And finally, containment and segregation. We use sealed equipment and physical barriers to keep combustible dust and ignition sources far apart. Now, just in case else fails, because sometimes Murphy's laws love engineering, we have explosion protection systems. First, explosion venting. These are panels that open during an explosion to safely release pressure, instead letting the system breathe out instead of blowing up. Second, explosion suppression. Here, sensors detect a rapid rise in pressure and immediately release the suppressant like CO2 or fine powders to stop the flame in milliseconds, faster than you can say kaboom. Lastly, explosion isolation. This stops the flame from traveling through ducts or pipelines to other equipment. Think of it as closing the doors before the fire can spread. Now, the engineering side is great, but humans are still part of the system, for better or worse. That's where administrative controls comes in. We start with good housekeeping. Regularly cleaning prevents dust buildup, and yes, your mom was right, cleanliness does save lives. Then training. Workers need to know the hazards and safe handling procedures of each equipment. You cannot control what you don't understand. Maintenance is also key. Faulty filters, leaks, or loose seals can also undo the best designs. And lastly, monitoring. Routine checks for ignition sources, dust levels, and ventilation efficiency. Because safety isn't one-time setup, it is a continuous habit. To wrap up, controlling hazards in fine powders isn't just about avoiding explosion, it's about designing smart systems and responsible behaviors. We combine engineering controls to prevent or limit incidents, and administrative controls to ensure people don't accidentally invite disasters back in. In short, keep oxygen out, dust down, and workers trained, and your facility stays in one piece. That's a win for everyone. So to bring everyone together, we journeyed from understanding why fine powders can be dangerous, to how and when they ignite, and finally what we can do to keep them under control. We started with the introduction, where we saw that even the tiniest powder particle can become the big hazard under the right or rather the wrong conditions. Then, we explore combustion fundamentals, learning how fire needs fuel, oxygen, and ignition source, a trio that we engineers try our best to break up. Next came combustion in dust clouds, where we saw how those tiny airborne particles can turn an ordinary space into a fireworks show in no one asked for. And finally, we wrap up with the control of the hazards using engineering and administrative measures to prevent, contain, or suppress explosions before they turn into catastrophic events. In essence, understanding the fire and explosion hazards in powders isn't just about safety, it's about respect. Respect for the science, for the system we build, and for the people who work with them. So, as we move forward in engineering practices, let's remember, safety isn't the absence of accidents, it's the presence of awareness, preparation, and a little bit of common sense. Thanks for listening, thanks for watching, I hope you learned something today. And always, stay safe, be healthy. Bye-bye!